Illustration of how to handle a situation where some foreign acid or base is added to the buffer solution. Here we have a buffer of acetic acid and acetate ions. Now, when you add HCl, you know that CH3CO minus is a conjugate base of the acid CH3COOH. So CH3CO minus is a conjugate base. And when you add something like HCl, then HCl will react with the base present in the solution. And due to that, acetic acid concentration will increase and acetate ion concentration will decrease. Right? Initially there was some acetic acid and acetate ion concentration. Now HCl is eating acetate ions, reacting with them rather. So acetate ion concentration will drop and acetic acid concentration will rise. So pH will change. How do we calculate the new pH? Just by knowing the new concentrations of these two, we can tell the new pH value. HCl is 0.2 moles. Then acetate ions 1 molar, 1 liter. That means 1 mole. Right? So 1 minus 0.2. 0.2 will react, 0.2 will be formed, but it was not 0 to begin with. It was how much? Acetic acid was how much? 1 molar, 1 liter, 1 mole. Right? So 1, 1, that was the situation earlier. 1, 1, both of them. Now the situation is 0.8, 1.2. Okay? And now you can calculate the pH using the standard Henderson's equation, pH equal to pK plus log of anion divided by acid. So I am putting up the working on the board. So there you are. The Ka value for acetic acid is 1.8 into 10 to the power minus 5. So minus log of that, then plus log of salt or anion, that is this 0.8 divided by acid, which is this 1.2, 4.57. So it's not that pH does not change. It's a question of how much can the buffer solution bear. How much can it bear? It has limitations. Let me know if you have any question regarding this, or we talk about buffer capacity. That's what I was talking about, how much it can bear. What is the buffer capacity? Buffer capacity is an indicator of this, how much can it bear. Now that definition takes into account per liter. Suppose you have a situation like this. It is an illustration. Suppose you have a situation like this, that you have half liter of buffer solution, and in that you are adding 0.01 mole of KOH, and you find that pH changes from 4.745 to 4.832. Then what is the buffer capacity? Moles of acid or base added per liter. Since you have 0.5 liters, you have to take double of it. 0.02 is what you need to take. That's a very important point. Divided by change in pH, which is very simple. Now this can be calculated easily, and it comes out to be 0.23. What do you think? Should it be large? If a buffer solution is good, then should the buffer capacity be large or should it be small? It should be large, because change in pH should be very, very small, ideally speaking. And if denominator is small, then this fellow has to be large. So larger the capacity, better is the buffer solution. Now you saw the application of common ion effect in case of multiprotic weak acids. You saw its application in case of mixed buffers. And now we are going to talk about solubility product. And in solubility also, you will see the effect of common ion. We begin with solubility product, and later on we talk about effect of common ion. In this discussion, we are focusing on salt. What do we mean by salt? Ionic species, which are supposed to give you ions when you dissolve them. All ions, all salts don't give you all full ions. If you think of NaCl, well, it's very nice. It gives you full ions, Na plus and Cl minus. But all salts don't give you full ions. And the reason is that they don't dissolve completely. They only dissolve partially or sparingly. So you can visualize that some part of the salt is lying somewhere inside the vessel, and while some part is floating in the solution. What is lying at the bottom of the vessel does not really participate. What floats, that's the one that participates. So all of it does not dissolve, but only slight part of it dissolves. So we are talking about those types of salts that are sparingly soluble salts. AgCl, typical example. Ag2CrO4, another typical example. So if you have some solid salt with you, you add it in water. So that's what you are doing. AxBy is the salt you have, which is solid. You are adding it in water, right? All of it does not go inside the water. Only some part of it goes inside or with water. So we need to use equilibrium. Right? Some part is lying at the bottom and some part is inside water. The part which is inside water, that's the one which ionizes. That's the one which ionizes. So effectively speaking, this part will ionize. Effectively speaking, you can write this. Suppose cation is this fellow and anion is that fellow. Then X particles of this, A is X, B is Y particles of this. Now why I am able to put this charge? That's pretty obvious, crisscross approach, A, Y, B, X, right? That's how you get the valencies, crisscross. So only that part which has dissolved, only that ionizes, right? The rest is lying somewhere at the bottom of the vessel. Solubility. How much is soluble? That's solubility. How much is soluble? Just think of it as a typical stoichiometric reaction. If alpha part of it goes, alpha X is formed, alpha Y is formed. If S part of it dissolves, X into S and X into S, what is getting dissolved is getting ionized, right? So if S part of it dissolves, then it ionizes and you get XS, these ions, and XS, these rather Y. This is Y I have used here. YS, these ions. Now S is in mole per liter. So S is just like concentration. But many times we can talk of solubility in terms of gram per liter also. But here in this I am using mole concept type of thing, so I have to use mole, 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 or molarity, molarity, molarity. If it is gram per liter type of thing, then one has to be careful. You can't linearly apply gram, gram, gram everywhere. So here when I write XS by S, it is molarity. S is in mole per liter. For any equilibrium, we can talk of equilibrium constant, Kc. Here also we can do that. So when we write the equilibrium law, Kc equal to that, then look at the denominator. You know the activity of solid? It's solid. So effectively speaking, this is what is called the solubility product. So it may look like ionic product type of thing. Ions are multiplied. So actually if you see, so many things come from chemical equilibrium discussion. Kc we defined there. Then for acids we talked about Ka. For base we talked about Kb. They also came from Kc. Then ionic product of water Kw. That was also nothing new. It came from Kc. Then Ksp also coming from Kc. And for Kc, the rule is that at a particular temperature, Kc has particular value. So all these fellows which have come from Kc discussion, they will follow the rule. Ksp will follow the rule. So Ksp is fixed for a particular salt at a particular temperature. If you change temperature, Ksp will change. Now looking at the top, if I use XS here and I use YS there, then I have this result. So that was a general discussion for something like AXBY. Any questions in this? Let me know, or I will illustrate for some specific cases like AgCl, etc. Fine. Here is the illustration for AgCl. So take some AgCl, try to dissolve it in water. Some part will dissolve, and that part which dissolves ionizes also, giving you Ag plus and Cl minus ions which are present in the solution. Now, if S part dissolves, S of this, when I say S part, now I am talking about molarity, not gram per liter type of thing. Molarity. So the solubility product would be just like ionic product. And Ag plus concentration is S, Cl minus concentration is S. So we have S square. That's it. Another illustration when it is not as simple as 1:1. Any questions in AgCl part? If you have, let me know, or we go for that. Fine. Lot of silver salts you will find in this discussion. So not 1:1, I can take this fellow, Ag2CrO4. So solid, aqueous, some part dissolves and that part ionizes, twice Ag plus, and then we have CrO4. minus minus. Now here if S goes molarity wise, then 2S is formed, S is formed. Solubility product is Ag plus, but this time power 2 will come. Just like in case of Kc, stoichiometric coefficients go to the power, Ksp has come from Kc only. So similar behavior it will show. That's it. But Ag plus concentration is twice S. And this fellow has S. So we have 4S cubed. Any question regarding this? Let me know. Okay. Now at a particular temperature, Ksp is fixed at a particular temperature. If you somehow increase the concentration too much for that temperature, Ksp has a fixed value at a certain temperature, right? Now somehow you are able to increase the concentration of ions. Maybe by adding something else from some other source you can introduce ions. This is the net ionic concentration. Doesn't matter from where they have come. So you can do that. And when you do that, this side tries to become too much, but Ksp cannot become too much. It has a fixed value. So obviously, left side, isn't it? Left side. Left side means going towards the solid. That means precipitation. So if you increase ion concentration too much, then it can lead to precipitation. Left side equilibrium shift. Now other extreme can be that you have very little of the right side. Maybe you got these ions from somewhere in very little amount. You got Ag plus ions from somewhere, you got CrO4 minus ions from somewhere, very little. And then you put them in some container. Now they are very small, such that this value is less than Ksp value. You can always multiply ion concentrations and you can get more than Ksp, you can get less than Ksp, you can get equal to Ksp. So from some other source, if you get too little Ag plus and too little CrO4 minus ions, such that this is less than Ksp of this fellow, then it won't like to form. It won't like to form. Because these concentrations are so small that this fellow is not formed. No precipitation. If they are in very dilute concentration. But if you somehow get Ag plus and CrO4 minus in huge concentration, such that this number becomes more than Ksp. This number becomes more than Ksp of this. In that case, precipitation will take place and you will get solid particles of Ag2CrO4. The third case can be that you get Ag plus and CrO4 minus from outside in just enough quantity that this product is equal to Ksp, exactly Ksp of this. This is the limiting case, and this will just lead to the commencement of precipitation. just the beginning. Right? If you get these fellows from somewhere else, some other source, and this product is meeting KSP value of this, precipitation will just commence, limiting situation. So when we discuss this thing, will precipitation take place or not, then believe this KSP thing. Just focus from wherever they have come, focus on this product and see if this product is more than KSP, less than KSP, equal to KSP. And then you can tell will the precipitation occur, will not occur, or is just about to occur. So KSP concept helps us to predict about precipitation of some particular thing when you have the presence of ions in the solution. To generalize this discussion, imagine these ions present in vessel. When these ions are present in vessel, this A plus Y and B minus X ions, calculate this number, right? Then check if that number is more than KSP, equal to KSP, less than KSP. If that number is more than KSP, it means solid will precipitate. If that number is less than KSP, no, it won't precipitate. It won't go to the left side. And if it is equal to, that's the limiting case. Yes. Now, effect of common ion on solubility. Again, let's talk about AgCl. AgCl does not like to dissolve much. So we are using equilibrium. We won't use equilibrium when we are talking about something like NaCl. KCl also same story. We won't talk about equilibrium just like NaCl. So KCl plus water, single arrow. K plus and Cl minus. When we talk about KSP of AgCl, then the total ion concentration is looked at. Doesn't matter who is supplying what. Now, KCl is already contributing to Cl minus ions. KSP will not change at a particular temperature. So the total Cl minus, total, has increased because of this. Hypothetically speaking, suppose in some unit KSP has some value, maybe 2 into 2, 4 some unit, 4 something 4 into something, 2 and 2, alone case. But now suppose KCl is giving 4 of Cl minus, 4 into 1 is 4. Now Ag plus, it means, can be 1 only, isn't it? Ag plus can be 1 only if Cl minus is 4 thanks to KCl. And Ag plus is coming from where? Coming from dissolved AgCl. That means dissolved AgCl is only 1 now. How much was dissolved AgCl earlier? Dissolved AgCl earlier was 2. That's how this 2 came and this 2 came. Now dissolved AgCl is 1. That's how Ag plus is 1. Right? So what has happened? AgCl was dissolving in 2 units, 2 into something, and now it is dissolving in 1 unit, 1 into something. So due to the presence of the common ion, the equilibrium does not like to go to the right side as much as it would have liked earlier. Well, it was never liking it, but it likes it even less now that there is some common ion. The common ion is further suppressing the dissolution process. Generally, this is the way you will handle the common ion situation. Say AgCl has solubility S. S is going. Let's talk of molarity. So S is formed. But suppose you also have KCl, and that is giving, take some number for Cl minus, maybe 0.1 molar. KCl solution was taken, 0.1 molar. So 0.1, right? 0.1. But solubility product looks at the total ions. Doesn't matter who is supplying what. So it won't be just S, it would be S plus 0.1. And that would be equal to KSP. So S into S plus 0.1, that is KSP. Solubility is suppressed due to the presence of common ion. That is the general situation. There can be exceptions. Any questions about this common ion effect in solubility? If you have, let me know. Now one more point here. While doing this type of case, we make approximation if it is justified, and S is going to be normally quite small, so it can often be neglected with respect to this thing. So what happens is that you have ease of calculation. S into 0.1 is approximately equal to KSP. And then you can find solubility, KSP upon 0.1 in this case. Very simple problem. Let's say we have AgCl's KSP given. Look at that number, -10, and that is at 25 degrees centigrade. You know, if K is less, it means the right side is less favored. We want solubility in water, pure water. We want solubility in water first. Now water means no common ion. So it would be as simple as S square equal to this, and under root will be the answer in terms of molarity. Sometimes you may be asked solubility in gram per liter. So after getting molarity, it can be easily converted to gram per liter. Here it is coming out to be 1.224 something into 10 to the power minus 5. Now let me introduce some common ion. Suppose now we don't have just pure water, but we have silver nitrate, 0.1 molar silver nitrate. Now while a lot of silver salts you will see in this discussion of solubility product, there is no problem with silver nitrate. Silver nitrate is single arrow. Now we are interested in the solubility of AgCl, and we expect that the solubility of AgCl should fall in the presence of silver nitrate. Now, if now the solubility is S, it will be S plus something, S plus 0.1. Solubility product won't change. So S plus 0.1 into S, that is equal to 1.5 into 10 to the power minus 10. Look at the previous answer. What was the order of S? 10 to the power minus 5 was the order. So doesn't it make good sense to neglect S with respect to 0.1, 10 to the power minus 5, that is supposed to be better because there was no other common ion. Our answer now should be less than the previous answer. Neglecting S with respect to 0.1. So 0.1 S is approximately equal to but it should be a very good approximation. Now look at that. 10 to the power minus 9. So from 10 to the power minus 5, it becomes 10 to the power minus 9. That's becoming really very bad. And now suppose I change the solution from silver nitrate. In silver nitrate the common ion was Ag+. Now I want to make chloride as the common ion. Case 3. 0.01 molar NaCl. What would be the solubility of AgCl in 0.01 molar NaCl solution? That is your assignment question. Solubility of AgCl in 0.01 molar NaCl solution. That's your assignment question. We stop now.